Hi, I'm Sahong, and I'll introduce our paper titled HiQL, Offline Goal GCRL with Latent States as Actions. This is a joint work with Debo, Ben, and Sergey. Unsupervised or semi-supervised learning has recently been shown to be very effective and scalable, like language models in NLP and representation learning in computer vision. Then what would be an analogous way to leverage a large amount of unlabeled trajectory data in robotics or reinforcement learning? We believe offline goal control is one such way, because it provides a way to learn a variety of useful goal-reaching behaviors without any reward labels or additional environment interactions. More specifically, the goal of offline GCRL is to learn to reach any goal state from any other state from a static data set D by learning a goal condition policy. The most straightforward approach to offline GCRL is as follows. First, we feed a goal condition value function using any value-based offline RL algorithm like CQL or HIQL. This is an example of an optimal goal condition value function. The closer to the goal, the higher the value. And then we extract a policy to find actions that lead to higher values. This can be easily done with this kind of a weighted regression objective. While this looks sensible, there's an issue in practice, which is that the learned value function can be very noisy, especially in states that are far away from the goal. This is because it's really difficult to accurately estimate the distances between states and goals when they are very far away from each other. This becomes problematic when we extract a policy. In this policy extraction step, what we do is that, first, we compare the values of adjacent states, and then pick the action that leads to the highest value. But here it's wrong because of the noise, and we end up getting an erroneous policy. And this is even worsened in our offline setting because we cannot provide corrective feedback via environment interactions. To resolve this, our solution in this work is very simple. Instead of extracting one policy, we extract two policies from the same value function. Specifically, we first extract a high-level policy that outputs k-step-away subgoals toward the goal. For example, when k is 3, we compare the values of these 3 step-away states and pick the one with the largest value. This will likely be much more accurate than before, because the value differences among these subgoals are much larger than those among adjacent states, so it's more robust to noise. And then we extract a low-level policy to reach the found subgoal. To do that, as before, we just compare adjacent states and pick the best action. This will also be much more accurate than before, because we only need to reach very close subgoals where the noises are much smaller. As a result, even though both policies are extracted from the same noisy value function, the overall accuracy can be much more improved. This is the intuition behind our method HiQL. Its practical implementation is also very simple. First, we train a value function with any offline RL algorithm, like HiQL, and then we extract a high-level policy with weighted regression, and also a low-level policy also with weighted regression, and that's all. There are a couple of advantages of HiQL. First, these two steps are completely decoupled and are supervised learning, so they are very easy to train. And moreover, the value loss does not require any action labels, so we can pre-train it even with action-free video data. But there is one remaining problem. The high-level policy should produce subgoal states, and this can be very expensive in, for example, pixel-based environments. To resolve this, we propose a simple technique to learn subgoal representations. Our idea is just to parameterize the value function in this way and use this intermediate layer phi as a subgoal representation. So the high-level policy outputs a low-dimensional representation phi st plus k, which the low-level policy takes as input to output actions. In the paper, we prove that this simple technique learns representations that are provably sufficient for control. We applied HiQL to some challenging environments. This is an example of an ant-maze video of HiQL. Here the red circle denotes the goal, and we can see that the high-level policy learned to produce subgoals colored in blue toward the goal. HiQL even works in pixel-based ant-maze using our compact subgoal representations. We also evaluated HiQL on benchmark environments, and it achieved very strong performance in general. Especially in ant-maze, it achieves the state-of-the-art performance. HiQL works well in pixel-based environments as well, thanks to our subgoal representations. To summarize, HiQL uses the simple idea of extracting two pulses from the same value function, which we show significantly improves GCRL performance. Please check out our paper and website for more results and code. Thank you.